Voyager 2 is not racing toward one last great discovery. It is running out of the ability to tell us what it discovers. That is the part most people miss. A dead spacecraft can keep moving for a very long time. A stone can do that. A broken bolt can do that. But a spacecraft that can still measure, still point, still send a signal back across billions of miles of darkness, that is a different thing. That is not just an object traveling through space. Is less than number. And right now, Voyager 2 is somewhere between those two conditions. Not quite silent. Not fully alive in the way it once was. It is more than 13 billion miles from Earth, moving outward through a region we cannot visit, carrying instruments from another engineering age, and using a shrinking supply of power from radioactive heat. So the real drama is not sim. Most people hear the name Voyager and immediately think of distance. I understand that. Distance is easy to admire, even when we cannot feel it. We say billions of miles, and the mind does something funny. It nods, but it does not really picture the number. We say interstellar space, and suddenly we imagine a tiny machine drifting across a black stage, very noble, very lonely, very far away. Fine. That picture is not wrong. That diff. So I do not want to begin with the usual question, where will Voyager 2 end up? That question belongs to a much larger clock. Tens of thousands of years. Millions of years. Maybe longer, depending on what kind of path we care about. That is interesting, but it is not the urgent question. The sharper question is this: where will Voyager 2 still be when it speaks to us for the last time? Where will it stop being a scientific instrument and become only an artifact? That is the question that turns this from a travel story into physics. Voyager 2 was launched in 1977. I want you to sit with that for a moment. Not because the date is nostalgic, but because it tells you what kind of machine we are talking about. Its computers were not powerful in the way we now casually expect computers to be powerful. Its memory was tiny. Its processors were slow. Its instruments were built for the outer planets, not for half a century of work beyond them. And yet the machine is still doing useful science. That is not a miracle. I do not like using that word when careful engineering will do. It is what happens when people design conservatively, build redundantly, test patiently, and then operate the machine with almost unreasonable care. Space helped a little too. No rain. No rust in the ordinary sense. No wind shaking it every day. But space is not gentle. It gives you radiation, cold, distance, and time. And time is the one that always collects its bill. The early part of Voyager 2's story is famous, and it deserves to be famous. Jupiter, Saturn, Uranus, Neptune. 4 giant worlds, 1 spacecraft, 1 rare opportunity created by the arrangement of planets. But do not let the phrase rare alignment become mystical. There is nothing mystical about it. The planets move. Sometimes their positions make a route possible. A spacecraft can fall toward one planet, swing through its gravity, and leave on a new path toward another. We call that a gravity assist. It sounds like the planet gives the spacecraft a push, and in a sense it does. But physics keeps the accounts. The spacecraft gains energy relative to the sun, and the planet loses an amount so tiny that no one living on that planet would ever notice. It is not magic. It is bookkeeping with gravity. Voyager 2 used that bargain again and again. At Jupiter, it found a world that was not just a big ball with moons around it. It was almost a small solar system of its own, full of radiation, magnetic fields, volcanic activity, and moons doing surprising things. At Saturn, The rings stopped looking like clean classroom circles and became a complicated structure made of particles, gaps, resonances, and small gravitational arguments between moons. At Uranus, the magnetic field did not behave the way a neat drawing might have promised. It was tilted, offset, awkward. Good. Nature is allowed to be awkward. At Neptune, far from the Sun, Voyager found speed and weather where simple intuition might have expected a cold, dead calm. And then there was Triton, icy and distant, but still showing signs that the outer solar system was not a frozen museum. That is what exploration does when it is worth doing. It does not merely add facts to a list. It scratches the clean picture we had before. Before the spacecraft arrives, we have models. Some are good. Some are too neat. After the spacecraft arrives, the models have to answer to the object itself. That is the wonderful humiliation of science. You think you understand something, and then the universe says, not quite. But after Neptune, the story changed. There was no next giant planet swelling in the camera. No new blue disk ahead. No dramatic flyby waiting like a scene in a film. For a movie, that might feel like the ending. For physics, it was more like someone had changed the experiment. The cameras had done their great work. The planetary tour was over. Now the quieter question began. What happens when you keep going outward from the sun? That sounds simple, but it is not. The sun is not just a bright ball that lights the planets. It also blows outward. Not air, of course, but charged particles, a thin electrical wind carrying magnetic fields with it. Picture the sun breathing into space for billions of miles. Eventually that outward push meets the thin material between the stars. Not a wall. Not a border fence. More like two physical conditions pressing against each other. On one side, the sun dominates. On the other side, the galaxy begins to win. Voyager 2 crossed that boundary in 2018. The word boundary can be misleading, so let us be careful. It did not pass a sign saying now entering interstellar space. What happened was better than a sign. The instrument saw the environment change. Particles from the solar wind dropped away. Galactic cosmic rays became more important. Plasma conditions shifted. Magnetic behavior changed. That is how physics recognizes a place. Not by a label. By several measurements beginning to tell the same story. And here is why the last voice of Voyager 2 matters so much. It is now measuring a region that no spacecraft like it has measured in this way before, while slowly losing the power to keep measuring it. Its electricity comes from radioactive heat. Plutonium-238 decays, that decay produces heat, and a small fraction of that heat becomes electric power. There is no refill. No switch on Earth can make the atoms slow down or start over. The power declines because unstable atoms do what unstable atoms do. That is not misfortune. That is the machine obeying the same physics that made the mission possible. So the engineers face a problem that is brutally plain. The spacecraft has to spend power to survive and spend power to speak. It needs warmth in the right places. It needs orientation. It needs computers. It needs a transmitter. It needs instruments. But the budget keeps shrinking. Imagine a house at night where the generator is dying and you have to choose which room keeps the light. You do not turn everything off at once. You choose carefully. This instrument now. That heater later. A lower data rate. A different operating mode. It is not romantic. It is triage. But even after saying it plainly, something human remains in it. Each time an instrument goes quiet, Voyager 2 loses one of its senses. It is still there. It is still moving. But it hears less of the universe than it heard before. A magnetometer tells us about fields. A plasma instrument tells us about charged material. A cosmic ray detector counts particles that have crossed enormous distances before striking a detector built by human hands. These are not ornaments on the spacecraft. They are the reason it still matters. So the last place Voyager 2 speaks to us will probably not be some dramatic future destination with a name we can put on a poster. It will be this strange, thin, difficult region beyond the sun's main bubble, where the solar system fades into the local material of the galaxy. The last message may not feel grand when it arrives. It may be a weak signal, a narrow stream of numbers, received after light itself has spent many hours crossing the gap. But inside those numbers will be something extraordinary, a measurement from a place where the sun is no longer the main voice. That is why the ordinary sentence Voyager 2 will keep traveling forever is not enough. Yes, it will keep moving. But motion alone is not the miracle, and I will use that word carefully. The remarkable thing is that, for a short time in cosmic history, a machine made on Earth could enter the edge of interstellar space, feel the conditions there, and answer back. Not forever. Not loudly. Not with certainty that every instrument will survive another year. But for now, still enough. So our story should not begin with a spacecraft going far. That is too easy. It should begin with a spacecraft still able, just barely, to tell us what far is like. And when Voyager 2 finally stops speaking, it will not mean the journey has ended. It will mean the conversation has ended. The object will continue outward. Silent. Cold. Still obeying Newton. But the scientific life of the spacecraft, the part that turns distance into knowledge, is happening now. That is the part we should listen to while we still can. To understand why Voyager 2 will finally go silent, we have to begin with a slightly strange correction. Space is not really the villain here. The vacuum is not the thing that kills it. The darkness is not the thing that kills it. Even the enormous distance, by itself, is not enough to kill it. The real problem is quieter than that. It is less cinematic, but much more honest. Voyager 2 is being defeated by power. Not all at once. Not with a bang. Just watt by watt, year by year, the machine is losing the small amount of electricity it needs to keep being a spacecraft that can speak. That may sound less exciting than an asteroid strike or a sudden failure, I know. But this is exactly why it matters. A spacecraft in deep space does not need fuel every second to keep moving. Once it has been thrown onto the right path, Newton takes over. Motion can continue with almost no effort, because there is almost nothing out there to slow it down. But thinking costs power. Measuring costs power. Pointing an antenna at Earth costs power. Keeping a tiny electronic system warm enough to behave properly costs power. So the strange thing is this: Voyager 2 can keep traveling long after it can no longer be useful to us. Movement is cheap. Meaning is not. If Voyager 2 were close to Earth, maybe we would imagine big solar panels catching sunlight. That is the easy picture. Panels open, photons arrive, electricity flows. But Voyager 2 is not close to Earth. It is not near Jupiter. It is not even near Neptune anymore. Out there, sunlight still exists, of course, but as a power source it becomes thin and disappointing. The reason is simple geometry. Light spreads out. Twice as far from the sun means the same sunlight is spread over 4 times the area. Go 30 times farther than Earth, and the sunlight is roughly 900 times weaker. So solar power was never the real answer for this journey. Voyager 2 had to carry its own little fire, and that fire is nuclear, but not in the way people often imagine. There is no reactor inside Voyager 2 like a power plant on Earth. There are no control rods sliding in and out. No boiling water. No turbine turning somewhere in the dark. What it carries is simpler and in some ways more beautiful. It carries radioisotope thermoelectric generators. The name sounds heavy, almost like something from an engineering manual, but the idea is not hard. Inside them is plutonium-238. That material is unstable. Its atoms decay. When they decay, they release heat. So the plutonium becomes a long-lasting heat source. Not an engine pushing the spacecraft. Not a bomb. Just a slow, steady source of warmth that can be turned into electricity. Now, the next question is very ordinary. How do you get electricity from heat? At first, that sounds like a trick. Heat is just atoms moving around, so where does the current come from? The answer is that you do not use heat alone. You use a difference. One side of the generator is hot because of the plutonium. The other side is colder because it radiates heat away into space. Put the right materials between those two sides, and a voltage appears. That is the thermoelectric effect. It is not very efficient. Let us be honest about that. But it is reliable. No pistons. No spinning shaft. No complicated moving engine waiting to jam after decades. For a machine that has to survive where no repair crew can ever go, reliability is not a luxury. It is the whole argument. At launch, Voyager 2 had enough electrical power to run its systems and instruments. Not a huge amount. This is the part that makes me stop for a moment. We are not talking about the power budget of a city, not even a small house using many appliances. We are talking about a few hundred watts, carefully divided between computers, transmitters, heaters, sensors, and control systems. A civilization used a few hundred watts to visit Jupiter, Saturn, Uranus, Neptune, and then keep listening from the space beyond the sun's bubble. That is not magic. It is disciplined engineering. It is people arguing over every watt because every watt meant one more measurement, one more command, one more small chance to learn something. But the plutonium does not stay the same. Plutonium-238 has a half-life of about 87.7 years. That means that after that much time, about half of the original atoms have decayed. Not because each atom follows a little schedule we can watch one by one. A single atom is not predictable like that. But a large collection behaves with statistical precision. Half remains after one half-life. Then half of that after another. Since the heat comes from decay, less active material means less heat. Less heat means less electricity. And there is another problem too. The thermoelectric materials age. 50 years of heat, radiation, and time do not pass through a machine without leaving fingerprints. So Voyager 2 loses from both sides. The plutonium produces less heat, and the generator becomes less effective at turning that heat into useful power. This is where the story becomes less like a heroic adventure and more like a household problem, except the house is billions of miles away. You have a shrinking supply of electricity, and you have to decide what stays on. The spacecraft must keep pointing its high-gain antenna toward Earth, because speaking across that distance is not like shouting into a room. The beam is narrow. A small pointing error can make Earth miss the signal entirely. It also has to keep its electronics alive. The computers are primitive compared with a modern phone, but primitive does not mean optional. They receive commands. They manage data. They coordinate the machine. Without them, Voyager 2 is not an explorer anymore. It is just an object, and then there is warmth, which people often underestimate. Deep space is cold, yes, but the real question is what cold does to hardware. Fuel lines can freeze. Lubricants can behave differently. Electronics can drift out of their safe range. A heater using only a few watts may sound tiny in a kitchen. Out there, it may be the difference between a working spacecraft and a silent one. Then come the instruments. These are Voyager's sensors. They ask questions in hardware. What is the magnetic field here? What particles are passing through? What is the plasma doing? How does the galaxy press against the outer edge of the sun's influence? Each instrument turns a physical condition into a number, and that number becomes a message sent home. But when power falls, not every question can stay alive. That is the hard part. Imagine a laboratory where the lights grow dimmer every year and nobody can plug in a new cable. Nobody can replace the generator. Nobody can send a technician. You can only choose which experiment deserves one more year. That is what Voyager 2 has become. Instruments are turned off, not because they suddenly have no value, and not because the people on Earth stopped caring. They are turned off because survival and science are now competing for the same shrinking pool of watts. A heater matters. A transmitter matters. An instrument matters. But arithmetic does not care that all three matter, and even if Voyager 2 can still transmit, the signal itself has another enemy: distance. Radio waves spread out as they travel. The farther they go, the thinner their energy becomes. Twice as far means 4 times weaker. 10 times as far means 100 times weaker. So the problem tightens from both ends. The spacecraft has less power to speak, and the signal has farther to travel. Earth can build enormous antennas and listen with extraordinary patience, but even the best antenna cannot repeal geometry. At some point, the message becomes too faint, or the pointing fails, or the power falls below what the mission needs. Any one of those can end the conversation. So this is the strange ending of Voyager 2. It probably will not end like a movie. There may be no explosion, no final flash, no dramatic collision with something waiting in the dark. More likely, the ending will be smaller and sadder. One instrument goes quiet, then another. The spacecraft becomes simpler. It still moves. It still exists. But it has fewer ways to tell us what it is passing through. And finally, one day, the last useful signal may be too weak to separate from noise. Voyager 2 will keep going after that. It will continue outward for immense stretches of time. But for us, the speaking will be over. The machine will still be there, but the conversation will have ended. Now we have to be careful. With one little phrase, interstellar space. It sounds enormous. And of course, it is enormous. But it also tricks the mind. When people hear it, they may imagine black emptiness, perfect silence, a vacuum so clean that nothing is happening there. But that picture is too neat. It is the sort of picture we draw because it is easy, not because nature promised to be easy. Space between the stars is thin. Yes, unbelievably thin by ordinary human standards. But thin is not the same thing as empty. There are particles out there. There are magnetic fields. There is plasma. There are cosmic rays coming in from the wider galaxy. There are slow changes in density and pressure that would mean almost nothing to your hand. But everything to a spacecraft trying to measure where the sun's influence fades into the Milky Way. So let me put the sun in a different picture. Do not imagine it as a yellow ball sitting alone in a clean black room, because that is already the wrong starting point. Imagine it moving through a very thin galactic medium, a kind of almost invisible environment made of gas, plasma, dust, magnetic fields, and charged particles. The sun throws out the solar wind in all directions. That wind carries particles and magnetic field lines outward. It pushes, and the galaxy, through the surrounding interstellar material, pushes back, somewhere between those two influences. The solar wind loses its control, not because it hits a solid wall. There is no wall. There is no glass shell around the solar system. What changes is behavior. On one side, the particles and fields are mostly shaped by the sun. On the other side, they are mostly shaped by the galaxy. That boundary is what we call the heliopause. But even that word, boundary, can mislead us. Because boundary sounds too clean. It sounds like a line on a map. You step over it, and now you are somewhere else. Nature is usually not so polite. The edge of the sun's influence is messy. There are particles from the sun trying to move outward. There are particles from the galaxy coming inward. There are magnetic fields that do not simply arrange themselves like a neat diagram in a school book. There are pressure waves launched by solar storms, traveling outward for years before they reach that distant region. So the heliopause is not a fence, it is more like an argument between flows. And Voyager 2 flew directly into that argument. That is what makes Voyager 2 so valuable. We did not just look at the boundary from Earth and guess. We did not only make a model and admire the mathematics, we put a machine there. That sounds simple, but in physics, it is a very serious difference. A telescope can look from far away. A model can predict what should happen, but a spacecraft can sit in the environment and let the environment affect its instruments. It can measure the local magnetic field. It can count particles. It can detect waves in the plasma around it. One point in space may sound small, and yes, it is only one point. But one honest measurement in the right place can force 1,000 beautiful guesses to behave themselves. When Voyager 2 crossed the heliopause, the evidence did not come from one dramatic sign alone. That is important. In good physics, we like it when several different measurements begin to tell the same story. Solar wind particles dropped, galactic cosmic rays increased, the plasma environment changed, the magnetic field showed that Voyager 2 had entered a different regime. Each one by itself might invite argument. Together, they become much harder to dismiss. The spacecraft had moved beyond the main reach of the solar wind and into the local interstellar medium, but we should not picture this as Voyager 2 suddenly entering some pure, untouched galactic ocean. That would be too simple again. The sun still leaves traces beyond its own boundary. Its influence fades, but it does not vanish like a lamp switched off. Solar eruptions can send disturbances outward. Those disturbances can travel through the solar wind, reach the heliopause, cross into the interstellar medium, and later shake the plasma around Voyager. Think about that for a moment. Something happens on the sun, and years later, far beyond the main solar wind, an old spacecraft may detect the echo. That is not empty space. That is a physical environment with memory. The magnetic field is one of the key things Voyager 2 can still help us understand. A magnetic field in space is not decoration. It changes how charged particles move. It bends them. It guides them. It helps decide how cosmic rays enter the solar system. Before Voyager gave us direct measurements out there, we had models. Some models were elegant. Some were probably close. But a model is still a model. Reality has the annoying habit of having details. The magnetic field outside the heliopause did not behave like a smooth, quiet classroom drawing. It had structure. It fluctuated. It showed that the heliosphere is not a perfect bubble, floating peacefully in space. And this matters. Beyond our own solar system, every star with a wind may make something like this. A protective region where the star pushes against the surrounding interstellar medium around other stars. These regions are called astrospheres. Their size and strength may affect how many cosmic rays reach the planets inside them. That matters for atmospheres. It matters for radiation. It matters when we talk carefully about habitability. Not romantically. Carefully. If we want to understand planets around other stars, we should first understand the protective bubble around our own star. Voyager 2 is giving us one of the rare direct measurements from outside that bubble. Then there are cosmic rays. The name sounds dramatic, but the idea is simple enough. These are high-energy charged particles arriving from outside the solar system. Many are protons. Some are heavier nuclei. They come from violent processes in the galaxy, and they move at tremendous speeds. The heliosphere shields the inner solar system from some of them. Not all. It is not a perfect shield, but the solar wind and magnetic field change how many cosmic rays reach the planets. So if you only measure cosmic rays near Earth, you are measuring them after the sun has already modified the sample. That is like trying to understand the air outside while sitting inside a filtered room. Voyager 2 gives us a way to compare inside and outside. How much does the sun filter? How much gets through? How does it change? With solar activity, these are not decorative questions. They connect the sun, the galaxy, and the radiation environment of planets. Plasma is another part of the story, and I want to slow down here because plasma can sound like a technical word people throw in to make space sound complicated. But plasma is not exotic in the universe. Stars are plasma. Solar wind is plasma. Much of the ordinary matter we observe in astrophysics behaves as plasma. It is matter where charged particles are free enough that electric and magnetic effects become dominant. In plasma, waves can travel, fields can oscillate, particles can move together, not just as isolated little bullets. That is why plasma measurements matter. They help tell us density, disturbance, and how energy moves through the medium. Here is the funny thing about physics. The universe almost never gives us labels. It gives us effects. We infer temperature from light. We infer mass from motion. We infer density from waves. Voyager 2 can detect plasma waves and use them to understand the electron density around it. That may sound indirect, but indirect does not mean weak. It means you know the rule. Connecting the effect to the cause. That is much of science. Nature does something. You measure the doing. Then you ask, what kind of physical condition could have produced it? So where, really, is the last place Voyager 2 will speak to us? It is probably not a dramatic location with a name that sounds final. It is not a monument in space. It is this stretched region beyond the heliopause, where the sun's influence is fading, but not completely gone, where the local interstellar medium is close enough for Voyager to sample. and where the spacecraft still has enough power to turn conditions into data. That is the brutal practical question, which runs out first. The distance to a cleaner, less disturbed interstellar region, or the power to measure it. That is the kind of question I like, because it removes the romance and leaves the comparison. How far? How fast? How long? What instrument still works? And every year, the spacecraft becomes less like a full laboratory and more like a fading witness. That matters. When several instruments work together, you can compare changes in particles, magnetic fields, and plasma waves. You can see one event from different angles. But when instruments go dark, you lose not only data, you lose correlation. The story becomes thinner. The interpretation becomes harder. Voyager may still speak, but with fewer senses. That is why the real drama does not need exaggeration. Voyager 2 is not about to find a magical wall at the end of the solar system. It is not heading toward some hidden object that rewrites physics overnight. The real story is better, because it is real. It is an old machine, far beyond the main solar wind, still measuring a region no other active spacecraft can sample in the same way, while its ability to keep measuring slowly disappears. A spacecraft does not scientifically reach a place simply because its metal passes through it. A dead spacecraft can cross something wonderful and tell us nothing. No particle count, no field strength, no plasma density, no wave signature. For physics, the real destination is the last place, where nature still changes an instrument, and the instrument still whispers the result back to Earth. That is Voyager 2's final place, in the scientific sense. Not the farthest coordinate it will ever reach, but the last successful act of measurement. And that is why we should listen now. The galaxy will keep doing what it does. The plasma will still ripple. The magnetic field will still bend charged particles. Cosmic rays will still move through the boundary between solar and galactic influence. Nothing out there will stop. When Voyager stops, only our listening will stop. For a little while longer, distance and life overlap. Voyager 2 is far enough to tell us what outside the sun begins to mean, and still alive enough to report it. That overlap is rare. It will not last. Now we have to talk about the part of Voyager 2 that is easiest to underestimate, because it does not look dramatic. It is not the plutonium. It is not the old computers. It is not even the instruments that are slowly being turned off one by one. The most fragile part may be something you cannot hold in your hand at all. It is the conversation. A thin radio link between a small machine beyond the sun's main influence and a planet full of people trying to listen. And I want to be careful with that word, conversation, because it sounds sentimental at first. But here it is not only a metaphor. Earth sends a command. Voyager receives it, if everything works. Voyager changes its state, if the old electronics still obey. Then it sends back telemetry, science data, or just enough signal to say, in engineering language, I am still here. That loop has stayed alive for nearly half a century. Not quickly, not loudly, but alive. People sometimes say Voyager 2 is sending data home. And that phrase is useful, but it hides the hard part. Home is not sitting still. Earth is rotating. Earth is orbiting the sun. The receiving antennas are only in certain places on Earth, and they can only listen when the geometry is right. Voyager is not pointing a flashlight at a wall across a room. It is aiming a radio beam across more than 13 billion miles toward a moving target, using a spacecraft built in the 1970s, powered by a source that gets weaker every year. Say it that way, and the miracle becomes less mysterious, but more impressive. It is not magic. It is geometry, power, timing, and patience, all working at once. The spacecraft does not shout. It whispers. That is the plainest way to say it. The transmitter power is small by ordinary Earth standards. We waste comparable power every day without noticing it, in lights left on, chargers left warm, little machines doing almost nothing. But Voyager has to use its remaining power as if every watt has a job and every job has a cost. The high-gain antenna helps by focusing the radio energy into a narrow beam. That is good, but it creates another problem. A narrow beam must be aimed. And across deep space, a small pointing error is not small anymore. A tiny angle here becomes a huge miss over billions of miles. So a strange thing can happen. Voyager may still be functioning. It may still be producing a signal. It may even still have something valuable to tell us. But if the beam no longer includes Earth, then from our side, the spacecraft becomes silent. That is why attitude control is not just a technical footnote. It is part of the voice. I know that sounds almost poetic, but it is a very physical statement. If a person speaks while facing the wrong direction, the words may exist, but the listener may not hear them. Voyager has the same problem, only colder, slower, and less forgiving. It must know how it is oriented. It must use sensors and thrusters to keep the dish aimed toward Earth. It must do this while its power declines and its parts age. And no one can go there and tap the side of the machine. No one can open a panel. No one can replace a valve or clean a thruster line. We can only infer, command, listen, wait, and infer again. Now add time delay. This is the part that changes the feeling of engineering. Near Earth, light is so fast that we forget it has a speed at all. You turn on a lamp and you do not experience a delay. But deep space makes the speed of light feel slow. A command sent to Voyager takes many hours to arrive. The answer takes many hours to return. You do not press a button and see the result. You send the instruction into the dock, and then you wait. Did the spacecraft hear it? Did it decode the command? Did the relay switch? Did the heater turn off? Did the instrument change mode? On Earth, you might test a machine, adjust it, and test it again in minutes. With Voyager, the question itself stretches across time. Troubleshooting becomes less like repairing a machine in front of you and more like playing chess with a partner who answers hours later using only a few numbers and a fading signal. And the machine is old. That is not an insult. It is the reason we should respect it. Old electronics do not always fail in clean, polite ways. Old thrusters may not behave exactly as they did when the spacecraft was young. Materials change. Temperatures matter. Redundancy that looked abundant at launch becomes precious after decades. Engineers can reason from telemetry. They can compare patterns. They can make cautious choices. But they cannot assume that every backup system will wake up perfectly just because the diagram says it should. A diagram is clean. A 50-year-old spacecraft is not clean. It is real hardware, exposed to time, cold, radiation, and the slow exhaustion of its power source. This is where the final years become very different from the beginning of the mission. Launch was loud. Fire, vibration, countdown, acceleration. The ending is almost the opposite. A power table. A temperature reading. A carrier signal just strong enough to notice. A decision about whether one more instrument can be afforded. And I do not mean afforded in money. I mean afforded in watts. A few watts on Earth sounds like nothing. On Voyager, a few watts can decide whether a heater stays on, whether an instrument keeps measuring, whether communication remains stable enough to trust. The mission has become a world of small quantities, small currents, small thermal margins, small signals, small errors that can become large because there is no repair crew coming. So the hard choices are not between good science and useless science. That would be easier. They are choices among valuable losses. Keep one instrument alive, and another kind of measurement may disappear. Save power by turning something off, and you may accept a new risk somewhere else. Protect communication, and the scientific return may become narrower. This is not drama added by a writer. It is what physics does when energy runs down and distance keeps increasing. Every choice is a trade-off because the spacecraft has crossed from exploration by abundance into exploration by rationing. The radio signal also has to fight the simple fact that waves spread. We do not need a long equation to feel the problem. Imagine a sound spreading in every direction, becoming thinner as it travels. Radio is not sound, but the intuition helps. The farther the signal goes, the larger the region over which its energy is distributed. Earth catches only a tiny part of it. That is why the receiving antennas must be enormous, and why the signal processing must be so careful. We are not catching a shout from space. We are detecting a trace, something barely lifted above noise, and then asking mathematics to tell us whether meaning is still inside it. Noise is always waiting. The receiver has noise. Space has background radiation. Electronics fluctuate. The signal can be present and still not be usable. That distinction matters. A thing can physically arrive and still be practically lost. Voyager may transmit, and some electromagnetic energy may reach Earth, but if it is too weak, too corrupted, or too buried in noise, then we no longer understand it. The spacecraft may still be speaking, but the words dissolve before they become data. That may be how the ending comes. Not as one grand goodbye. Not as a clean final sentence. More likely, it will look uncertain for a while. A weak signal one day. A weaker signal later. More errors. Longer listening. More careful checks. Was the antenna pointed correctly? Was Earth listening at the right time? Did the spacecraft change mode? Was the noise unusual? Engineers will not want to declare the end too quickly, because with a machine like this, silence can have more than one cause. But after enough attempts, enough waiting, enough careful reasoning, the conclusion may become unavoidable. The loop has opened. The conversation is gone. There is honesty in that kind of ending. Nature does not owe us a cinematic farewell. Power declines. Distance grows. Signals spread. Noise remains. Pointing becomes harder to guarantee. Somewhere inside that combination, the last message happens. Maybe we recognize it only afterward. And that is why each signal before then deserves our attention. Not because it is sentimental, but because it is physically astonishing. A machine launched in 1977 sends a measurement from beyond the main solar wind. The signal crosses a distance light itself needs many hours to cross. A human-built antenna catches it. Electronics and mathematics recover it. And finally, somewhere on Earth it becomes understanding in a human mind. So when we ask where Voyager 2 will speak to us for the last time, the answer is not only a coordinate in space, it is a condition. It will be wherever Voyager is when enough things still work together one more time. Enough power, enough pointing, enough transmitter stability, enough listening on Earth, enough signal left above the noise. That is the final place in the scientific sense. Not just a location, but the last overlap between what the spacecraft can still say and what we can still hear. And until that overlap disappears, Every faint message is not routine. It is one more moment in a conversation that has lasted far longer than anyone had a right to expect. Eventually, Voyager 2 will stop speaking to us. Not because it has reached some dramatic wall at the edge of space. Not because the universe suddenly refuses to let it go farther. The reason is much simpler, and in a way, much more human. The spacecraft will run out of the practical things that make a mission alive. Power, heat, pointing, a working transmitter, a signal strong enough to cross billions of miles and still be recognized on Earth as something more than noise. The object will continue. That part is easy for physics. Once something is moving in deep space, and there is almost nothing rubbing against it, it can keep going for an astonishingly long time. But a mission is not just an object moving. A mission is an object that can still tell us what it is experiencing. That is the part that will end. And I think this distinction matters, because people often mix these two things together. They ask where Voyager 2 will go, and that is one question. But they also ask where it will speak to us for the last time, and that is a very different question. A silent spacecraft can pass through space for millions of years. It can drift through the galaxy like a tiny piece of old machinery. It can be near this star or that cloud or some region with a beautiful name. But if it cannot measure, and if it cannot send the measurement home, then for science the conversation has already ended. That may sound severe. I do not mean it cruelly. I only mean that science has a very practical requirement. Something must be turned into information, and that information must get back to a mind capable of asking what it means. Think of it in a very ordinary way. If you throw a bottle into the ocean, the bottle may travel farther than you ever will. It may cross currents you will never see. It may pass fish, storms, darkness, warm water, cold water. But if there is no message inside it, and no way for it to report what it passed, then it has traveled, yes, but it has not explored in the scientific sense. Voyager 2 is different because, for nearly half a century, it has not merely traveled, it has reported. It has converted planets, moons, magnetic fields, particles, plasma, and distance itself into evidence. That is the living part of the mission. And that is the part we are slowly losing. So the last meaningful place for Voyager 2 is probably not some romantic future landmark. It is not the farthest point it will ever reach. It is not the most dramatic star it may someday pass near. It is not the Oort cloud as a grand final chapter, even if the spacecraft may one day move into those distant regions where icy bodies live in the sun's far outskirts. The last meaningful place is much closer to now. It is the region where Voyager 2 still has just enough power to notice something, just enough stability to aim itself, and just enough voice to send the result back to Earth. That place is the interstellar region just beyond the sun's main bubble, where the solar wind no longer rules in the same way, and the galaxy begins to press its own conditions against the remnants of our star's influence. That place does not look like the kind of destination people put on a poster. There is no blue planet filling the camera, no rings, no volcanoes, no strange moon casting a shadow across clouds. In fact, to the human eye it may seem almost empty, but that is only because our eyes are poor instruments for this kind of place. Voyager 2 is not watching scenery now, it is listening to conditions. Plasma, magnetic fields, energetic particles, the thin pressure of the local interstellar medium. These are not dramatic words for most viewers. I understand that. A picture of Neptune is easier to love. A magnetic field reading does not immediately make the heart jump. But scientifically, this quiet data may be among the most valuable things Voyager 2 still gives us, because it comes from a region where almost no human-made instrument has ever worked. And here is the part I find easy to miss. The ending probably will not feel like an ending at first. It may not be one clean final sentence from the spacecraft. It may be a weak signal one day, then missing data, then another attempt, then a period of uncertainty. Engineers may ask whether the spacecraft is truly gone, or whether the problem is temporary. They may try commands, they may wait, they may listen again. The end of a real machine is often not theatrical, It is diagnostic, it is patient, it is full of checks, doubts, and careful language. Nobody wants to declare the last word too early, and maybe that is fitting, because Voyager 2 has never been a symbol first. It has been a working instrument first. I also want to be careful about sentiment here. Voyager 2 is not lonely. It does not know that it is far from home. It does not feel cold. It does not feel proud. It does not have courage. Those words belong to us, not to the machine. But that does not make the mission less human. It may actually make it more human. The spacecraft carries no feeling of its own, but it carries the results of human choices. We built it. We aimed it. We borrowed gravity from planet after planet. We waited years for answers. We listened through noise. We kept the mission alive long after the original plan would have sounded almost too small for what it became. The meaning is not inside the metal as a feeling. The meaning is in the questions we placed inside that metal. That is why the golden record has such a strange weight. It is not useful in the ordinary scientific sense. It will not tell us the density of plasma. It will not measure cosmic rays. It will not keep the antenna pointed. But it says something about the kind of creature that built the spacecraft. We knew, even then, that the chance of anyone finding it was fantastically small. Space is too large. The spacecraft is too tiny. The timescales are almost absurd. Still, we put a record on it. Sounds, images, greetings, music, little traces of Earth. Not because the universe promised to listen, but because once a species learns how to ask questions, it has trouble staying silent. There is something almost uncomfortable about that. Long after the transmitter is dead, the record may still be there, bolted to a silent spacecraft, moving through darkness with no working conversation behind it. The instruments will be cold. The computer will no longer answer. The signal will be gone. But the record may remain, not as a functioning message in any practical sense, but as an artifact of intention. A sign that, for a brief period on one small planet, matter arranged itself into beings who could wonder where they were, build tools, and send one of those tools outward with both instruments and a greeting. But I do not want to make the ending too sad. Sadness is part of it, yes, but it is not the whole story. The real wonder is not that Voyager 2 will eventually fail. Of course it will fail. Everything we build has limits. The wonder is that it worked for so long, across such distances, under such narrow margins. It used gravity assists, radioactive decay, thermoelectric power, radio communication, celestial mechanics, and an enormous amount of human patience to do one thing very well. It made the unreachable measurable. That is enough. We do not have to exaggerate it. We do not have to pretend it is alive. The actual achievement is already large enough. So when we ask where Voyager 2 will speak to us for the last time, the honest answer is not the most poetic one. It will speak from wherever the remaining power, the remaining orientation, the remaining transmitter strength, and the remaining listening on Earth overlap for the final time. That is the real boundary, not a painted line in space, not a mythic edge of the solar system, a practical overlap between physics and communication. For a little while longer, Voyager 2 is still in that overlap. It is still somewhere, and it can still tell us something about being there. That is what makes it a mission, and not merely an object. One day, the overlap will close. Voyager 2 will continue outward, but it will no longer be our instrument. It will become something quieter, an artifact, a piece of Earth moving through the galaxy, still carrying a record, still following a trajectory shaped by choices made decades ago, still obeying the same physics that allowed it to leave the planets behind, but no longer answering. And maybe that is the cleanest lesson it leaves us with. Distance by itself is not discovery. Motion by itself is not knowledge. Discovery begins when the universe is measured, and the answer makes it home. So listen while it still speaks. Not because the signal is loud, it is not. Not because the final moment will be dramatic, it probably will not be. Listen, because every remaining packet is part of a conversation that no other spacecraft has had in quite the same way. A conversation between Earth and the space beyond the sun's wind. And when that conversation ends, Voyager 2 will keep going, but we will have to let it go as a mission. The machine will continue through the dark, the data will remain here, and for a little while longer, before silence takes over, it is still answering,